I have this defective Presonus, what is this? Studio 1824C. I'm not sure yet what's wrong with it, but I wanted to see inside first before I power it on. Well, I have a clue of what might be wrong with it. First of all, Jamicon or Jamicon, and this one has a domed top, which is not a good sign. Alright, a quick measurement in circuit on these suspicious caps. This first one's supposed to be 1000 micros. It's measuring 300. A good ESR, but that's beside the point. This smaller one is a wonderful cap X on, and it should be 470. It's measuring 410. A bit low. I'm going to take it out and measure it again, but I'm probably just going to chuck it. There's just no point. These Jamicon are giving me strange readings because I think there's more than one of them on the same rail. So I'm going to pop one or two of them out and spot check. As for the other ones farther down the board, those are also all in parallel on the what I suspect is V plus and V minus rails. Yeah, I think they're fine. They probably don't work as hard as the ones in the switching power supply, so I'll worry about those a bit later. Okay, I replaced a few of the worst offenders. I am a bit concerned though that I'm measuring very low resistance between what I assume is some of the power rails and ground. It's looking like 35 ohms, 50 ohms depending what I'm probing. So I'm going to power this from a lab power supply with a current limit, and I'm going to increase, I'm starting at 2 volts just to see how it behaves. I'm assuming it'll take at least 5 or 6 volts to turn on. There's a MOSFET on the input. Okay, I really wanted to see what was going on the 1 volt rail because the DMM was giving me some strange readings, and this is why. So it's reaching 1 volt and something's happening, then it's discharging again. So that's not too bad. At least I know I'm probably not destroying the CPU. Let me probe around. It's on the underside. This is a bit easier. What is that? 2, 4, yeah, 5 volts, but with lots of. Okay, so. Okay, nice. It's enumerating. That's very good. Okay, next test. I have signal generator giving me 0.76 volts. And I'm gonna test input channels. Starting at 3 just because they're lined up along the back. This is number 4. Very good. Next I'm going to test output channels. Well, line outputs. This is main, and it is control. Okay, so the bar graph indicates the input signal, and this controls the output that you can't see, but it's plugged into my DMM. Now I'd like to measure the equivalent input noise specification and if it matches the specs. So in the manual it says EIN equivalent input noise minus 128 dBu. This means that with the inputs connected with only this resistor here and gain set to maximum, we're going to get this amount of equivalent noise. Now you can't directly measure this quantity. It's a bit indirect, and I'll get into that. dBu units, these can be confusing when you're not used to working with those different standards. It does get confusing. It helps to go on one of these pages with notes and converters to get a hang for it. So 0 dBu is 0.77, usually written as 0.775 volts RMS. So minus 128 would mean there's an equivalent of, what is that, 3, well, it's a very small voltage. You can't just bust out your DMM and measure this. Here's a different view of what we're doing and how we're going to get that measurement. So this is the audio interface, and on the USB side, it gives out samples that are simply numbers, and they're usually written as dB below full scale. So 0 dB full scale would be the absolute maximum value that it can produce. Now the designer of this thing knows exactly how many volts at this point correspond to 0 dBFS. That could be 3 volts or 5 or probably actually lower than that. But we don't know that. And then this gain stage here, adjustable from -15 to +65, well, that can vary a bit also. So we have a bunch of unknowns in here. So we're going to proceed differently to sort of black box this whole thing. For the equivalent input noise, or EIN spec, it's applied with the preamp set to maximum gain, so +65, and then they connect RS here, which is 150 ohms. Then they measure the noise spectrum here, and the designer of this thing knows, well, if it was, say, -150 dBFS, well, they know the scaling and the gain, so they can tell us the input here was -128 dBu, for example, which is I think a few microvolts, so really small, and there's no way you're going to be able to measure that directly. Now we can't do the exact same thing, so we're going to start with a signal generator here, set to 1 kilohertz or whatever. Then a simple divider here. Now I set the bottom resistor to about 150, and the top I think was 150k. So it's about 1,000 to 1. And we're going to shoot that right in. And with my voltmeter, I'm going to measure this point here. And I'm going to calculate the divide ratio so that I don't have to measure this node here on the input. So with that, that's going to give me a first approximation of the input voltage corresponding to a certain value. I usually use a slightly lower value from the calibration, -3 or -6, because with the noise and the peak samples, like the RMS values are lower than the peak values. And if you clip, then your measurement's not going to work. So that works pretty close to fine, but to do a slightly better job, you need to take into account that the input isn't a perfect high Z infinite impedance input. It's actually got, and on purpose, an equivalent input impedance here, which means that we need to compensate for this a bit, and that's actually not really difficult. So the first thing I do is I select a test resistor, and I'm going to measure voltage at this point. This then is the input with equivalent input impedance. So I'm going to take first measurement with this disconnected, and second measurement with it connected. And then I think, if my math is right, the equivalent input impedance would be resistance times, and it turns out for the Presonus, this comes out to about, I think it was 850 ohms. And since my divider is 150k, so that's my divider, this whole thing has an equivalent output impedance of, well, it's 150 in parallel with 150k, so it's roughly going into an input impedance of, what was that, 820? Yeah, ohms. So it makes a small difference, and I just threw it in the spreadsheet and took it into account. And the good question to ask would be then, well, when I reduce the impedance of the divider, but if I put, let's say, 10 ohms and 10k, then it's still a negligible load for the signal generator, and then my output impedance is suddenly 10 ohms. Then 10 ohms in conjunction with, what was it, 180 or so, and that's basically no difference. This load is almost 100 times larger than... That's the smart thing to do, and what I'm going to do next time. So let's see how that goes. I'm going to write this down. I'm reading 52 point, let's call it 0.22. And when I connect the preamp, I read 44.77. I got the gain maxed out, and initially you'd think this is kind of a disappointing noise level, but that's because the input is open, and if I plug in a 150 ohm stub, that should go way down. Well, reasonably down. Mind you, the below 20 Hertz can be ignored, so I'm just gonna set the range like this. What I'm interested in to compare with the data sheet is the A weighting value here, so minus 87, but those are dB from full scale, and as I said, we want to know what full scale is. Now I'm going to connect instead a signal generator, well, the attenuator. Okay, so I'm reading minus 6.04 from full scale. Now I can go into here and, well, I don't enter my DMM value, but I calculate the actual input, so 2 point something divided by my divider ratio, and that is 1.995 millivolts. Thank you. So that means that on the input, if I apply 3.99 millivolts, that would give me 0 dBFS. And now that the software is calibrated, I can change the scaling to dBu and disconnect my signal generator, connect that 150 ohm dummy plug. I got some averaging, that's good. The scale is correct, and I'm reading minus 128.6 dBu with A weighting. That's real close to the specs. I'm sorry, I gotta show some numbers now. So I tested all channels here, and I did basically what I showed earlier. So for every channel, I noted first voltage before the divider, calculate the theoretical open no load divider voltage. Then I have a corrected divider value. It takes into account the loading of the preamp input impedance. It's not a big difference, but it counts. And I compute a bunch of stuff. Then in REW, I noted down the dBFS value, and interestingly, channels 1 and 2, and I got them highlighted for this reason, they had a slightly lower gain. I'm pretty sure that's because they have a different input structure, because of the switching between high Z for instruments and regular microphone preamp. And then, like, this column is a separate test. I plugged the 150 ohm dummy plug for this, noted down a value of dBFS also from REW, and then calculate the EIN. That would be the EIN value that matches the data sheet or the manual, and indeed it's really close. I think they gave 129, and there's a very small spread even for those channels 1 and 2. The gain and everything compensates, so what I'm really measuring is the preamp noise, which is pretty good, minus 129. I also have this going on at centered at 3.215, somewhere here, and as I change frequency, I did the math, that's where it ends up. And this is 1 times the frequency, so plus and minus the carrier. I had a theory that maybe that 3.2 kilohertz was coming from maybe the display here, which is a LED bar graph, and it's most likely multiplexed. I didn't really want to take it apart right away. I don't have any of those fancy EM probes, but I do have those old AM radio kits for kids, and I kept a couple of parts. So ferrite antenna, a little transformer to step up the voltage, hopefully, to this crystal earphone. So holding this to my ear and moving it around, I can hear the power supply working, and when it's off there's nothing, but as I have a signal connected there, and as I increase the volume, every time an extra segment turns on I can hear it. I'm gonna try rigging a microphone to this because it's interesting. Okay, hopefully this works.